I put the words or the number 7 billion there because according to the what I read in the newspaper, this was the weekend where the world's population just increased past 7 billion. So it's kind of a important day in terms of world population. I'm going to talk about population a little bit a week or two from now when we're talking about global warming issues and environmental issues. But you know, every scientist that's looked at this issue would probably define the holding capacity of the planet. And there's the number of people that could live here sustainably. Everyone would define it differently depending on how they do the calculation. My guess would be that the holding capacity of the planet's probably about half that number, probably about 3 or 4 billion. So now I may be way off on that, but by my estimate, we've long since shot past the holding capacity, which means that we're basically using up resources that cannot be renewed. So eventually something will have to adjust, either a very different kind of living or come down to a different population. Anyway, it's a troublesome number. What else? Well, we got to experience our first nor'easter. It was quite exciting. And of course, one of the remarkable things about these storms, they come up the coast, but they end up mixing warm and cold air, right? So you get the warm air coming from the south with lots of water vapor being lifted, producing lots of precipitation, and yet the cold air comes down from the north, from the west side of the storm, wraps around, and allows you to keep that snow, which was formed aloft by the ice phase mechanism, allows you to keep it as snow all the way to the ground. So even in this time of the season, which is generally not so cold, we had pretty good snowfalls because the cold air down from Canada allowed that snow to keep as snow as it fell all the way to the ground. The unusual thing about it was a little bit earlier than we typically have nor'easters, and that combined with the fact that as the last 20 or 30 years have gone by, we've gotten warming in New England, which has kept the leaves on the trees later and later and later. So this was the first, in my recollection, this was the first real nor'easter that's come while most of the leaves were still on the trees. 20 years ago, the leaves were off the trees easily 2 weeks ago. Mid-October, everything was down, but now we still have the leaves, and now we get our first nor'easter. So it's a subtle indication, maybe not so subtle, that things are changing when you can get a nor'easter coming while the leaves are still on the trees. Interesting. Any comments on that? Anybody get out and try skiing in the snow? It was very wet, wasn't it? So it was more of a sloppy snow than anything else. Any questions before we get started today? Okay. Well, we had a little bit to finish up on our discussion of ice, and we hadn't quite finished the mountain glacier section, so I've gone back to this first diagram from that section. And I wanted to remind you about the definition of a tidewater glacier. That's when a glacier comes down to the sea so that pieces can break off and form icebergs. And some, of course, don't get down that far. And maybe I'll get the lights off for this. An interesting set of glaciers is the North and South Patagonian ice fields down in the southern Andes. The North Patagonian ice sheet is here, the southern one is here, it's larger. And many of them actually calve off their glaciers in these big lakes to the east into Argentina. So if you were to go down there and sign on to a tourist boat that would take you up to the calving glaciers, they would be in these lakes for the most part, rather than in the fjords coming in from the Pacific Ocean. So that's kind of an interesting place. But remember, they're calving in fresh water there. They're not really, so I guess I wouldn't really call them tidewater glaciers, although you could argue it either way. They're calving into water, but it's freshwater lakes rather than rather than seawater with tides. Flying over it, you get to see these snow-covered mountains. You get to see some of the ice breaking up into crevasses as they begin to flow over a bend. Wherever they've got to drop over a sudden break in the slope, they often break up into these deep crevasses. And of course, they're covered with snow, but if you were to fall into that, you would fall down 50 or 100 meters and be lost. But you can see the flow streaks, these medial moraines, follow it down to where the calving occurs. It's a bad picture from an aircraft, but there's a lake there, and the icebergs are calving into the lake. And you see it here as well. You see these various moraines, medial moraines going down, and then they break off into the little lake down there. Now, there's been a trend in the amount of ice in mountain glaciers, and it's negative most places. This shows a number of different parts around the world where you've got mountain glaciers, and it's kept track of their mass since 1960, and the units here are meters of water equivalent. So it's not how deep the snow or the ice is on the glacier, but if you were to melt it into liquid, how deep would be. That's a convenient reference because snow can be of different densities, and even compacted snow, depending on how tight it's been compacted, may not reach the full density of ice. So for this kind of mass balance calculation, it's more convenient to, in the end, describe it as a loss in a depth of water equivalent. And a little bit hard to follow the colors, but in Patagonia, where I was just pointing, we've had some of the largest drops, 35 meters of water equivalent decrease in the thickness of those mountain glaciers. Alaska and the coast mountains have decreased rapidly as well. And the northwestern USA, for example, Glacier National Park, named after its glaciers, is having one of the most rapid decreases. And the word there is if you want to see the glaciers in Glacier National Park, you'd better go there in the next 5 years because they're diminishing pretty rapidly. However, there are some glaciers that are not changing very much. For example, in the Arctic, and again, I'm not sure of the color codes here, but it looks like the Europe and the Andean glaciers. This would be the southern Andes. This would be the rest of the central Andes. They are not changing so dramatically, at least not until the last few years. So it's a mixed story, but mostly strongly negative for the trends on those mountain glaciers. To wrap up, I want to go back and look at Greenland. We've already talked about it a little bit, but just to summarize some of the changes that are occurring in Greenland. So here are some of the glaciers coming off of the main Greenland ice sheet as a function of time from 2000 till almost the present day. And we looked at the Jakobshavn one. We spent some time talking about those. I haven't shown you the other ones, but those are, I did show you the Petermann up in the northwestern part. And for the most part, these are negative. Some very strongly negative, some not so strongly, but generally the glaciers are retreating. This is in units of square kilometers. And so basically it's not keeping track of thickness now, but the area as it decreases, generally negative. And we saw Petermann's glacier. So when that drops off, they decrease the area estimate of the Petermann glacier. And some would argue, well, that's not a significant loss because that'll refill eventually, but that's how they've done the calculation. And then we looked at Jakobshavn before and saw that its calving front was retreating with time as well, and that shows up on that time plot also. Now, there's another thing we can investigate about Greenland, and that is the amount of surface area up on the ice sheet that has meltwater in the middle of the summer. And what's shown, so you can fly a satellite over, look down, and by the way light reflects off the ice sheet, you can determine whether or not the snow is wet, whether it's got melt water mixed in with the snow. And in 1992, the pale area was shown to have meltwater in the warm season, and now 2005, even this deeper red area. It's only the diminishing white area that is free of meltwater, and that's an indication that the climate is changing as well. What happens to that meltwater? Some of it just stays there and refreezes the next winter. Some of it runs off in this rather remarkable phenomena called a moulin, which is basically a hole that develops in the ice sheet that allows surface waters that are melting in the summer to drain and fall a distance of perhaps a kilometer or so down to the base of the glacier. And then it'll flow along the base of the glacier out to the sea. So this is an example of one of those moulins up on the Greenland ice sheet, water then draining down into this hole that takes it down to the bottom of the glacier. Any questions on that? That's a summertime phenomenon, of course. Recently, we've got a new technology to keep track of what's happening to Greenland and other things around the world. It's called the GRACE satellite, and maybe you can make out the acronym here: Gravity Recovery and Climate Experiment. That's GRACE. And it consists of two satellites moving around the planet very close to each other, with a laser beam going from one to the other, doing accurate laser ranging. So you know within a millimeter or so the distance between those two satellites as they move. Well, as the Earth is not uniform in its density, the continents have mass, other things have mass concentrations that make the gravity field of the planet a little bit irregular. And by sending a satellite around that feels that gravity and keeping track of how the distance between the two satellites varies during the orbit, they can map out these gravitational anomalies around the surface of the Earth. And this is an exaggerated, what they've done is take a globe and in 3 dimensions kind of made it knobbly so that it shows you where the higher mass concentrations are. So this kind of irregular gravity field is what GRACE can detect as it goes around. Now that satellite's been in orbit for a few years now, and one of the applications of it is to look at not just the gravity concentrations near Greenland, but how they've been changing in time. And that's what's shown in this diagram. So 2 plots are shown, one for southeast Greenland, that would be this area here, the other for northwest Greenland up here. The time runs from 2002 to 2010, and this is the centimeter of water equivalent thickness removed from, or missing from, that part of Greenland over that period of time. And for southeast Greenland, putting a straight line through there, you get about -8 centimeters per year of water equivalent loss. And for northwest Greenland, it's about -7 centimeters per year. So the two values are roughly consistent. That tells you that the overall mass of the Greenland ice sheet is decreasing. You can do calculations with these numbers and figure out how long it would take before it would all be lost. It'd be quite a number of years because you know, these ice layers are quite thick, 1 kilometer or more. But nevertheless, it represents quite a bit of mass loss. And when that water melts and goes into the sea, of course, that raises sea level a little bit. So, and that's a calculation you can do as well. If you know the area of Greenland and how much this is decreasing per unit time, you can use the surface area of the oceans to compute how much that is going to raise sea level. Any questions on that? So, well, that's the end of the story on modern ice, current ice on the planet. We can take a few minutes if there are any questions about any of the things that I've covered with regards to ice in the climate system. Anything? Yeah, Julia.
Glaciers are always associated with mountains.
That's right. I would say the word glacier usually implies moving ice, moving gravitationally. So if you've got an ice sheet like Greenland, And through the gaps like here and here, where the ice can squeeze out and come down to sea level, that would be a glacier. You wouldn't refer to this as a glacier. This is an ice sheet, right? But where it's squeezing and flowing down to sea level, that would be a glacier. Or if you have a mountain glacier, a small mountain glacier with sliding gravitationally, that would be a glacier as well. So just don't use it with respect to a large ice sheet, and you'll be safe on the terminology side of things. Other questions on this? Okay. Well, we're going to shift gears a little bit. We're going to talk about how climate has been changing with time. And for this, you should be reading chapter 13 in your book. The author of the textbook has done a good job with 13. He's made a little different set of choices than I've made about what to emphasize. But I think the combination of the two, chapter 13 and Aaron's, and my presentation here today, and this will spill over into Wednesday, will give you a good introduction to how the climate is changing on the Earth. And I've made a decision to focus on the last 5 million years. And the reason for that, well, there are really three reasons for that. One is the continents have pretty much been in their present position for the last 5 million years. So we don't have to worry about the continents moving around. Second of all, this has been the period of time in our planet when humans have been evolving to our current form. So it's not so distant in the past that we're not engaged in it as a species. This is the period of time when we have been coming on to, evolving to our present form. And I guess third, we're looking for a period of geologic history where there's been significant change in climate in order to make the subject interesting. But also, one of the reasons for studying past climates is to provide a context for future climate change. And to provide a good context for future climate change, you would like to look at a period of Earth history that had significant climate change. And we certainly have it over the last 5 million years. So that's the reason why I've decided to focus just on the last 5 million years. There's a number of subcategories or subjects I'm going to be treating today and tomorrow. Today we'll probably only get through maybe the first 2 or 3 of these. We're going to start with a brief overview of the climate of the last 5 million years. Remind me, how many have had a geology course? Just a few of you. So you know something about this time scale, and I've mentioned it once or twice before as well. This is the geologic time scale. The Earth is something like 5 or 6 billion years old. This goes almost back to that level. The Precambrian is where we didn't have life in the form that would leave a fossil record, nothing with bones or shells or anything like that. There was life there, and there's certain types of physical fossils that are left, but not the actual remains of the organisms. Then you go through a series of rapid evolution as you come up through to the present time. We're not going to talk about dinosaurs. The dinosaurs died out right about there, probably with an impact from a large meteorite. Instead, we're going to focus just on these last 3 periods, the Pliocene, the Pleistocene, and the Holocene, taking us from approximately 5 million years up to the present. I showed you this plate tectonics diagram once before. Coming up in time, newer, 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 and newer. This takes us to the Cretaceous, which is here, 65 million years ago. we're jumping up now factor of 10 younger than that. So pretty much the continents are going to be in their current state for this last 5 million years. So we don't have to worry about any of this. If a continent has a record of a different climate, it's not because it was at a different latitude. It's because the climate was actually different on Earth at that time, not just the continents sliding around under the climate zones. Questions there? All right, so just a few words about these three periods. The mid-Pliocene, 3.3 to 3 million years before present, similar continental locations to today, but a significantly higher global temperature, maybe 2 to 3 degrees Celsius for the average global temperatures. Much more remarkable than that, though, was that the high latitudes were much warmer than they are today. There was a little bit of ice on Greenland, but not a real ice sheet. Because of that lack of ice, that sea level was about 25 meters higher than it is today. And for these reasons, there is quite a flurry of research going on right now about the Pliocene, because it's a possible analog for what the Earth will be like about 100 years from now with global warming. I'm going to talk about global warming next week, but this is really excited a lot of interest, this idea that maybe there was a period in the past we could look at to see our future, in a sense. Now, whether that turns out to be an accurate analog, I would say, remains to be seen. But that's one of the reasons why there's so much current activity about the Pliocene. Yes? So a million years before present. Million years before present. These were some of the mammals we had in the Pliocene era. Saber-toothed tiger and the woolly mammoth. As I say, no dinosaurs. That was 60 million years ago. The Pliocene vegetation. Now, there's no legend on this diagram, but the author wanted to make the point that the normal forests that we have here in mid-latitudes at that time extended all the way up into the Canadian archipelago, up into Alaska. Areas that are now tundra had forests very much like the ones we have here in Connecticut. So it really was a period of time when temperatures were much warmer at the higher latitudes than they are today. Then we'll jump to the Pleistocene, which is 2.6 million years ago up to just 12,000 years ago. One of the problems with paleoclimatology is we've got to deal with these vast stretches of time. It's a little bit hard sometimes to conceive of how long ago that was and how recent this was. But we'll be working on that today and next time, trying to give you all a better understanding of how these time scales work. The Pleistocene was possibly the coldest period in Earth history, although there have been discussions of periods of time hundreds of millions of years ago that may have been colder. But at least in recent Earth history, in the last, say, 100 million years or even 200 million years, probably this was the coldest period in that part of Earth history. As we'll see, there were lower carbon dioxide concentrations in the atmosphere than there are today. And throughout this 2.5 million year period, there were periodic advances and retreats of ice sheets and mountain glaciers. So it wasn't a single ice age. In a sense, it was a large number of ice ages with brief warm spells in between. If you averaged, however, it certainly was a very cold period of time. Surprising, because we just came out of the Pliocene, which was warmer than it is today. Then we go into the Pleistocene, which was much colder, and then we're going to bounce back out and talk about modern climates. I've written here Milankovitch pacing because the advance and retreat of these ice sheets seems to have been controlled by slight adjustments in the Earth's orbital parameters, the so-called Milankovitch theory of climate change. And I'll talk about that. And this period of time, 2.6 to the present, includes most of human evolution, at least the species that have Homo in front of them, as I'll show you in just a minute. And the last glacial maximum, the last of these ice sheet advances, was about 14,000 years before present. And it was just after that that I'll take the official end of the Pleistocene period. So I'm kind of defining the end of it as being the end of the last glacial advance. Here is a diagram showing human evolution. There's a time scale up here in millions of years ago. So here is today, 1 million, 2 million, 3 million years ago. The prefix A, Australopithecus, is on these brown species indicators. And then you get to the Homo prefix, and that really takes you from 2 million years up to the present. Homo sapiens, however, are only in the last couple of 100,000 years. So climatologically then, the Pleistocene goes from about here to about there, getting a little bit of Homo sapiens in it, and most of the other ancestors of modern man. So be sure you have some understanding of this when we're thinking about paleoclimate, so you can make the necessary connections between human evolution and the change in climate. Any questions on that? If there's any anthropology majors or people that have had an anthropology course, keep me honest on these things. I'm not much of an expert on human evolution, but don't feel afraid to speak out if I say something wrong about that. I'm going to come back to this diagram later on, but it suits the present purpose as well. It happens to be data from a Vostok ice core, and I will describe later how this data is gathered and interpreted. But for the time being, let's take it at face value. Here's a plot of temperature change from the present day back to 400,000 years ago. So here is today, and of course, by definition, present change year before, temperature change from present, that's right about zero, because here's the present day. About 10,000 years ago and earlier, we were in a much colder period of time. That's the last glacial period. Then there was another brief interglacial period about 130,000 years ago. Then a long glacial period, another brief interglacial, and so on. So when I talk about the Pleistocene as being a period of ice advances and retreats and significant climate change, this is what I'm talking about. On average, it was much colder than the present day, typically 4 or 5 or 6 degrees Celsius colder than the present day, but there were other interglacials. There were other brief periods of warmth. We're in one today, and about every 125,000 years back through this record, there was another brief interglacial. And that'll give you a sense of what I mean by this great variability that occurred within the Pleistocene period. At the last glacial maximum, in other words, right about here, about 20,000 years ago, although you can take it a little more recent than that, LGM is the abbreviation for last glacial maximum. This was the distribution of continental ice sheets. It doesn't show Antarctica, but Antarctica still had its full ice sheet at that time, and Greenland. But now look, in addition, you've got an even larger ice sheet over North America called the Laurentide ice sheet, and then a large one up over Scandinavia and northern Russia as well. So the number or the aerial extent of large continental ice sheets was much larger 14, 15, 20,000 years ago than it was today at the end of that the last glacial maximum. So really a dramatically different climate than we have today. This has been one of the biggest paradigm shift in the earth sciences in the last 200 years, was to convince us, ourselves, other scientists, and finally the general public, that this recent period was so different climatologically than the one today. If you go back and read the scientific literature from the period 1900, 1910, 1920, there were violent arguments in the scientific literature about whether this could really be true, that this short time ago there could have been massive ice sheets over the continents. Now we're certain it's true. We have many, many lines of evidence that convince us of that, but it was quite a big deal at the time. Okay, then the third geologic period that I want you to be familiar with is the Holocene. This is defined as the period of from 12,000 years before present to the present day, and it is the current interglacial period. In other words, the current non-glacial period. It has modern humans, the development of agriculture, a nearly constant climate, and nearly steady sea level during that period of time. So if you're looking for a reference point from which to consider or compute climate change, this is a possible candidate. Now, it's only 12,000 years, but still, that's quite a large time, and for some purposes, that might be a good reference point for defining climate change. But be careful, not everyone will agree with you on that. Some people might say, no, you'd want to perhaps go back a much longer period of time and integrate over all of those fluctuations in the Pleistocene, or maybe even include part of the Pliocene in your definition of a normal climate. This will haunt us, this idea of what would be the usual or the normal climate. It's almost an unanswerable question. Climate has changed so dramatically over geologic history that it's real hard to find a time that you'd be considered normal. This might be the best chance for that. Questions there? Okay, so there we have the Pliocene, the Pleistocene, and the Holocene, at least a brief introduction to those. Oh, here's a plot of the Holocene temperatures. This is thousands of years before present. This goes back to 12,000 years, which is the beginning of the Holocene. And temperature, there's a lot of different proxies that are considered here, and they all give somewhat different interpretations of past climates. But if we take a look at the thick black curve, which is the average of all of the different proxies, here we are coming out of the last ice age, reaching a value about 10,000 years ago, which remains roughly constant to the present day. However, these fluctuations have excited a lot of discussion. For example, this slightly warmer period here is often referred to as the climatic optimum, between about 8 and 5,000 years ago. So some would argue when I say that the Holocene climate was constant. It wasn't exactly constant. There were some fluctuations within it. Okay, so that's step one, getting those three time periods out on the table. There's lots of paleoclimate methods. We're not going to have time to talk about these, but I want to spend the rest of the period today talking about geomorphology. That is, looking at the landscape to deduce past climates. In a way, this is the most fun because we can do it ourselves. As we drive around the country, look out the car window, we can begin to see these landscape features that can be interpreted as evidence of climate change. So I want to spend quite a bit of time on this because it's the one that we can really have fun with and do it ourselves. I'm going to focus on surface evidence of the Pleistocene ice ages and look particularly at these 5 geomorphologic features. A terminal moraine is that pile of debris that marks the end of a glacier. Remember, a glacier is moving, carrying material along underneath it. melting at the front. So it's like a conveyor belt. It's bringing material and then the glacier leaves, but the material piles up. So if a glacier has a fixed terminus for a number of decades, it will build up a pile of rubble, rock and soil at the end of it. And then if that glacier were to retreat, you'd have no glacier here, but you would have that terminal moraine left as a marker, as evidence of where that glacier was. So that's the importance of the terminal moraine. It shows you where the previous end of a glacier was, if it was there at least for several decades or a few hundred years. Now here's one here. Here's a mountain glacier coming down into a lake. And here at the other end is the terminal moraine. So at an earlier time, this glacier filled in the lake and ended right there, and the debris it was carrying underneath it piled up to form that moraine. So we see it today, we can say, ah, that glacier has retreated because its snout used to be right there at that location. That's the beauty of the terminal moraine. It gives you this recent history of how far the glacier had extended. And for scale, here's a fellow standing on top of a pile of rubble. The glacier is nowhere to be seen. It's retreated up the valley, but this is where the snout of that glacier was. Now, there's some other things that happens underneath a large ice sheet that get revealed when the ice finally melts and moves back. Well, okay, I've said it wrong, didn't I? Move back. A glacier never moves back. Its terminus may retreat, but the glacier, the ice itself, is either stationary or is moving forward. When you go into a warm period and the glaciers retreat, they never do it by sliding that glacier back up the valley. Be very clear on that. It's only that the apparent end of it may seem to move back, but the ice will continue to be flowing from left to right here as the terminus moves from right to left. So be very careful about your terminology on this. Here's a terminal moraine left behind by that. There's an esker that I'll define in just a moment, and there are some drumlins that I will define in just a moment. An esker is a river flowing underneath the ice sheet, that gets partly filled up with debris, and then when the ice sheet melts, you're left with this little pile of debris where the river was. So the river, instead of being a depression in this case, as we're used to seeing, because it was a river up inside a glacier, actually leaves an elevated tongue marking where that river was. And here's a nice example of one up in Manitoba of an esker. So an ice sheet covered this. There was a river underneath the ice, and the debris that collected in that sub-ice river, then when the ice melted away, left you with that esker. Glacial striations, you can see them here in New England, scrapes on bedrock indicating that a glacier has slid over that particular part of rock. Usually underneath the ice there are chunks of rock embedded in the ice, and so you're scraping these embedded chunks over the bedrock, leaving a scraping mark. And you can tell what direction the glacier was moving. Well, it's hard to distinguish that from that, but at least you know it was either moving in that direction or in that direction from the direction of those glacial striations. Sometimes they can be deeper grooves, as you see in this piece of rock here. So that tells you that a glacier has scraped over this terrain. The glacial erratic are easy to spot. A very large boulder sitting on a bedrock that doesn't match it in terms of rock type. So it's foreign. It didn't come from here. It's been moved from some other place. And now if it was a small rock, you could say, well, maybe water could have moved that. But if it gets to be this size, there's nothing there for scale, but that's 2 or 3 meters in height, water could not have moved that large rock. So that had to be a glacier that moved it. So the word erratic means it's a large boulder in a place that has different rock type than the boulder itself. So it didn't come from there, it was carried in by somewhere else. Sometimes you can trace these back and find out where they came from, and that will give you a direction of ice motion. Here's another in Denali National Park and in Calgary, examples of glacial erratics. You can spot these pretty easily up in Canada. A drumlin is a hill that has been shaped by a glacier sliding over it. It's got usually a steep end and a less steep end, indicating the ice flow in this case was from left to right. So it scrapes off material here and then deposits it on this long tail back here. Here's a drumlin seen from the air. So the glacier was flowing from left to right in this case. Here's a bunch of them. I guess the farmers have planted fields in the flat terrain, but they've left forests on some of these drumlins. And then here's a field of drumlins up in Canada seen from a satellite. And it's pretty easy to guess which way the ice flow was. It was from upper left to lower right, forming all of those drumlins. So that's a little bit of what you can look for as you drive around to convince yourselves that there was a big ice on the landscape not too long ago. And this is what it looked like. So I want to spend a few slides just describing what the Earth was like during this last glacial maximum, roughly 20,000 to 14,000 years before present. In addition to Greenland and Antarctica, there was this giant Laurentide ice sheet, an ice sheet in the west coast called the Cordilleran ice sheet. But look, Alaska was, at least northern Alaska, was still free of ice. That's a bit of a surprise. However, there were also large ice sheets in Scandinavia and northern Russia as well. When you look at the drumlins and the glacial striations and the glacial erratics for the Laurentide ice sheet, you can work out a sense of motion, how the ice was moving, and this is what you come up with. The little arrows indicate what local evidence tells us about the direction of motion of the ice sheet. Down in our part of the country, it was from north to south, but up in northern Canada, actually, south to north. So it seems like there's a dome of ice here with a center somewhere around here, and the ice is then spreading out gravitationally away from that center. That's the view, or that's the vision you get when you see a map like this. Gravity is doing the spreading, and the high point must have been somewhere in the middle here with ice moving out in the different directions. One of the reasons they put a different name on the Cordilleran ice sheet because you see some eastward movement here, which conflicts with what the Laurentide ice sheet movement is doing. So there must have been a seam here along the Rockies where those two ice sheets were kind of butting up against each other. Questions on that? That's the Laurentide ice sheet. Now down here in New England, we've got this remarkable feature called Long Island to look at, as well as Martha's Vineyard in Nantucket. When the ice sheet came down here and it moved offshore and spent a long enough period of time to build up a terminal moraine, then retreated slightly and built up another terminal moraine. So there are two terminal moraines that now make up Long Island, Martha's Vineyard and Nantucket, as well as Cape Cod. All those features are basically terminal moraines left over from the last glacial maximum. So over New Haven here, we probably still had several hundred meters of ice sliding southwards, but then it tapered off and the terminus was roughly here for a long enough period of time to have built up two substantial terminal moraines at those locations. So we've got evidence right outside our front door that this ice sheet was overhead not that many years ago. Questions on that? Okay. Well, now we need to get a little more quantitative about climate change. And I won't be able to finish this, but let me say a few words about it, and then we'll cut until Wednesday. But we have to get more quantitative about climate change. We have to have records that we can go back uniformly in time to see how things are changing quantitatively. And one of the best ways to do this is by looking at the stable isotopes of water. And I wanted to remind you about what I mean by isotopes and how we're going to use them climatologically. You remember that an isotope of a chemical element is defined as an analog to that element that has an extra neutron or more in the nucleus to give it an added mass, but without any change in its electrical charge. So for example, hydrogen is normally one proton with electrons going around it. The most common isotope of hydrogen is called deuterium. It has a proton and a neutron in its nucleus, so it's got double the mass, but the same charge. The same charge means it behaves chemically like its parent. But that extra mass makes it behave a little bit differently when it comes to changing phase. With oxygen, the dominant, let's say the parent isotope of oxygen has a mass of 16, 8 protons, 8 neutrons in the nucleus. However, it's still oxygen if I add 2 more neutrons to the nucleus. Now it becomes oxygen 18. And these are the particular isotopes I'm going to be talking about next time with respect to looking for clues for climate change, particularly deuterium versus hydrogen and oxygen 18 versus oxygen 16. So I can make up new water vapor molecules now. If I make water from two normal hydrogens and a normal oxygen, it's going to have a mass of 18. 16 plus 1 plus 1, that's 18. If I replace one of the hydrogens with deuterium, that's going to give water with a mass of 19. If instead I keep the 2 hydrogens as hydrogens but replace the oxygen 16 with oxygen 18, I get a mass of 20. Turns out that these heavier isotopes of water have a slightly lower vapor pressure. This means they evaporate more slowly and they condense more readily. And this is what gives them, what provides to us information about how the hydrologic cycle was working in the past by looking at the ratio of these 2 isotopes. I'm out of time today, but before Wednesday, if you could spend a few minutes reviewing your high school and college chemistry about the nature of these isotopes, that'll put you in a good position to understand the lecture on Wednesday.